All right, so before the break, we saw the architecture of the CNN. How do we do the forward pass? We were looking at how do we do the back propagation, and so that we can train the algorithm, train the network, determine the values of all of these parameters, which were initially randomly initialized, right? Okay, so the key thing was, for example, this equation over here. So let me see if everybody followed this equation, right? As we were doing the forward pass, okay, so Cn of 2 is basically right here. This is where Cn of 2 is, okay? N could be 1, N could be 6, N could be 4, right? This output over here, as you can see, there's an activation function involved. But further, it's summing 4 convolutions over here from the previous layer. So this is what it did, sum of the 4 convolutions. So this is a 2D convolution. And then we add 1 bias to the whole thing, and then we pass it through the activation function. So this is how we did in the forward pass, right? Now, as we are going reverse, so let's pretend we've already computed the delta up to this point, which, as we discussed, is pretty straightforward. We go based on the loss, compute delta here, multiply by W transpose times derivative of the activation function, we know the delta here, times W1 transpose will give us the delta over here. There's no activation involved over here. We distribute the deltas to 4x4 matrices, meaning do the reverse of the flattening process. Then we simply divide each one of these values by 4 and put it over here. We multiply by the derivative of the activation function. So this part, hopefully everybody sees, is straightforward. Okay. So the question is, how will we compute? Let me see if I can create some room over here. How will we compute partial L over partial K? P, Q, P could be 1, Q could be 3, whatever for the layer 2. So pretend UV, because this U will vary -2 to 2, or 1 to 5, whatever the case may be. Okay, so anyway, so the question is, how do we create this, right? As you can see, for us to go backwards, what we need to do is, we already know the forward equation for the delta over here. So this basically has to be put into this equation. So meaning the delta up to this point. So delta up to this point further has to be multiplied by partial over partial KPQ of 2. Which partial are we taking? Whatever we did in the forward pass. So if I put this whole equation from here to here, put it over here, so that's essentially what we are, that will give us the delta that we need for the derivatives of these. Once we have the delta over here, then obviously that's the gradient with respect to the loss up to this point. Then we can add it by multiplying it with the learning rate, meaning minus the learning rate, whatever the original value was, and we can adjust it, right? So the rest of the work becomes trivial. Okay, so now the question is, what is the derivative of this thing with respect to, in our case, what did we have, Pn or something, with respect to Pn as an example. Okay, so there's one thing, it's difficult to explain, but let me see if I can clarify this. So let me create some room. Okay, let's take a look at the convolution process, what it's doing. See, the convolution process, what it's doing is, For example, I'm going to magnify this 12 by 12 and 8 by 8. So here's a 12 by 12. Here's an 8 by 8. Okay. So pretend we put a 5 by 5 kernel over here. Okay. And then remember, we'll multiply to each one of these values, and then it will produce one answer over here. You guys agree? Okay, then what will we do? We'll shift it 1 pixel to the right, do 5 by 5 multiplication addition again, and that will produce the second value in the output. This is in the forward pass, right? That's what the convolution does. Okay, now let's pretend in this 5 by 5 kernel, there's some value ij. For example, I could be 1, j could be 1, I could be 1, j could be 2. So this is one of the values over here in the kernel. Okay, my question to you is, was this, let's just focus on k11 as an example, the very first value in the kernel. Was it involved in computing the first value?
Yes.
Was it involved in computing the second value?
Yeah. We're starting at 0 or 1?
No, the same k11.
No.
Why not?
Because we are shifted.
If we shift it, we still are multiplying by the same kernel, right?
0.
Yes? Is this confusing? Let me see.
Yeah, okay. If it's the kernel, yes.
Yeah, so I'm just talking about one of the kernel values. Let's pick the, if this is our kernel, let's pick the very first value. Regardless, we call it K11 or K00, whatever, doesn't matter. Okay, this first value of the kernel, my question is, was it involved in computing the very first output? Was it involved in computing the second output? Third output? All of them, exactly. So once we go back, if there were multiple paths, because remember we are trying to compute the gradient with respect to this particular value. So all of those have to be accumulated over here. So that's the tricky concept. Okay, once you recognize this, then it's piece of cake. So what I'm trying to say is, what this becomes is the partial L over partial KP2, or doesn't matter, whatever indices we pick over here. So this basically becomes I equal to 1 to 8, j equal to 1 to 8, then whatever was the delta, let me call this delta star. So whatever delta we have computed up to this point, okay, so this will be delta star, multiplied by partial by partial, what did I have over there, Pn. Okay, so let me also call it Pn so that there's no confusion over here. Pn over here, and now I'll write this P equal to 1 to 4. Equal to minus 2 to 2, equal to minus 2 to 2, Cp of P of 1, R minus U, J minus V, K of Pn, UV of 2, plus Bn of 2. And okay, somewhere there was a sigmoid, and let's pretend sigmoid has already been absorbed. So sigmoid has already been absorbed in this delta. So I don't have to further do a sigmoid. Okay, so this has been absorbed into delta. Meaning once we created it, we already had multiplied by the output times 1 minus output. Okay, so this is already absorbed. Okay, so anyway, if we did the partial now of this particular term, because remember that's with the one particular P and N, right? So what you will see is, what will happen is, and this is also for one particular value of U and V. So this is for one particular value of U and V. So what will happen is, all of this, because we are taking the derivative with respect to this, right? So this one will disappear, because this is like, sorry, my mistake. So think of it as if I said, what is the derivative of A of x with respect to partial x? Isn't it just A, right? So the net result will be, okay, if I can write it maybe one more time over here. Net result will be I equal to 1 to 8, j equal to 1 to 8, per delta star, delta star. Okay, so this will just, all the summations will go away because we are taking the derivative with respect to this, and also for one particular value of u and v. Okay, so this will simply become Cp of I minus u j minus b. And the derivative, again, with respect to b is 0, so nothing shows up over there. Okay, so if you agree with me up to this point, Cp of p, Cp of p, 1. If you agree with me up to this point, then let's try to take a look at this particular equation over here. C, okay, try to create one more room over here. Okay, if you recall, once we were taking a look at a 2D convolution, right? Okay, so suppose we were doing something, let's say y of ij equal to summation. Okay, so remember this might look like, pretend this is going from uv equal to something, right? So this will look like, for example, let's say x of, I'm just writing it in general, I minus u j minus b. Okay, let's say h of ij. Okay, so this is what a typical convolution looks like. Okay. So if our variables over here are u and v, take a look over here, in proper convolution, they are being subtracted from whatever was the value over here. So if you take a look over here, okay, in C, is this some kind of convolution going on? Okay. See, the only problem is if this was u and this was v as an example. Okay, then do you see like there's a minus u and minus v, just like over here? Then it will be a convolution of the two particular quantities. But the problem is the sign is opposite over here. Okay, so if we rotate it by, this by 180 degrees, what happens is this changes to Cp p of 1, and it becomes u minus I and v minus j. Okay, so then this particular quantity simply becomes equal to delta star convolution with Cp of p1. So that's the conclusion, that the delta up to this point, delta up to any one of these points, sorry, the derivative of this loss with respect to this on all of these is simply convolution of whatever this was over here with this particular value. Okay, let me see if I can further clarify this for you. Okay. To further clarify this, okay, what's the size of CP of 1 as an example? 12 by 12, right? On this side, what's the output size? Okay, let me see if I can, okay. If I'm trying to create partial loss over partial KPQ, meaning this, any one of these. Okay, first, forget about all the math that you looked at. Just if you tell me what would be the expected size of this? What will be the size of this matrix? Okay, if you're confused, let me ask you another question. Okay, if we computed partial L over partial W2, what will be the size of that matrix?
Same as W2.
Same as W2, 10 by 30.
Yeah.
Okay, if I did partial L over partial W1, what would be the size of that?
Same as W1.
Same as W1. So now, if I'm trying to compute partial L over partial KPQ, one of these,
Same as delta.
The same size.
Same.
5 by 5.
same as what?
Delta TQ.
C1.
Same as the kernel, right?
Delta.
Because this KPQ is basically one of the kernels. And what's the size of the kernel in our example?
5 by
5 by 5.
5 by 5. So do you agree this has to be 5 by 5? After we obtain it correctly? Okay, so now the question is, how, if you take a look over here, there's a 12 by 12 delta over here. On the input side, okay, you'll see there's 8 by 8 feeding in, right? Okay, so if I did partial L over this one, how can I get 5 by 5 out of a 12 by 12 matrix and 8 by 8 matrix? Okay, so let me write it down if it's confusing. Okay, so do you guys agree, first of all, this delta star, which is the delta over here, is 12 by 12? Everybody okay with this one? Right? Okay, now remember this, there's some kind of convolution going on, and we are producing let's see. Let's go over here on this convolution, right? So we have 8 by 8 as the output. So this is 8 by 8, right? After we do the convolution. This is 5 by 5. Okay, forget the delta star for the time being. And on the input side, CP1, as you can see, is 12 by 12. So moving forward, this makes sense. Do the convolution, we'll get 8 by 8. Right? 12 minus 5 plus 1. So the forward pass, does it make sense from here to here? Okay, now let's go the backward pass. So what we are trying to say is, we want to determine the value of this kernel. This is our kernel K. So how can we do, what's the relationship between 8 by 8 and 12 by 12? Okay. What if I gave you a 12 by 12 matrix? Okay. And I said the kernel is 8 by 8. If I did a convolution of these two, what will I get?
5 by 5.
Won't I get 5 by 5? So our final result that we got over here, which was basically delta star is 12 by 12. Okay, do a convolution with CP1. Okay, I have a mistake there. That should not be, okay, one of them has to be 8 by 8.
Delta star is 8 by 8.
A mistake. Okay, 8 by 8. So that becomes the convolution. Okay, sorry, this is not delta star. This is the, okay, once we have the delta star over here, okay, that's the actual input over here. Okay, so yeah, slight error I have in my development. Okay, delta star over here will be 12 by 12. Okay, then basically we are taking the output 12 by 12 over here and doing the convolution with this, sorry, my mistake, this is 8 by 8. We are taking the 8 by 8 output over here and doing the convolution with the CP1, as you guys saw over here, CP1 over here. Okay, so this is a convolution between deltas. Okay, this should not be there. So this is a convolution between the CP1, which is 12. No, this is right. This is right. Okay, yeah, sorry, everything is fine. Yeah, my numbers I initially said were wrong. So this is correct because this is what the math is doing. Okay, so let me summarize it again. Okay, what's the size of delta star in our equation?
8 by
8
8.
by 8.
8 by 8. So you guys agree this is 8 by 8. So this is 8 by 8, right? And this is the convolution operator. Sorry, right now it's a multiplication, but once we rotate it by 180, then it changes to a convolution. So this, everybody agrees, is 8 by 8. What about this part?
12 by 12.
This is 12 by 12. If we do a convolution of 8 by 8 with 12 by 12, what do we get?
5 by 5.
5 by 5. And that was the derivative with respect to the k. So once we have the k, then like we can basically go kpq of 2 equal to kpq of 2 minus the learning rate. So the rest of it stays the same. Times partial L over partial kpq. So what I'll do is I'll write it a little cleanly so that you guys can actually see all the steps. So, so let me summarize it. See if everybody sees, because it is complicated, so let me go over it one more time, okay? So what we did is, okay, first we looked at the forward pass. Okay, so we looked at, for example, the equation for up to, what did we call it, CP somewhere, CN? Yeah, so up to here. So first we looked at in the forward pass, what is this equation? Okay, and that's what we came up with in the forward pass. This is the equation. We apply the activation function by summing the 4 inputs, and then which is the convolution between the kernel and the previous output. So if you can understand and follow that in the forward pass, right? So then in the backward pass, like I said, for the same part, there are 2 concepts involved. Okay, the first concept is, sorry, my diagram is getting messy. Okay, the first concept is as we are doing the convolution on this CP1, okay, and producing the output. Okay, so the concept was each one of these kernel values is involved in all the 8x8 numbers over here. So this will be 8x8 numbers. Each k of ij is involved in computing these. Okay, so that means once we go reverse, because there were 64 paths going from 1k to the output. On the backward pass, we have to accumulate those 64 things to compute the actual gradient. Okay, and this is where this I equal to 1 to 8, j equal to 1 to 8 came into play, right? Whatever was the gradient up to this point, okay, we called it delta star. Then further, we have to multiply by the derivative with respect to kpn. So k is missing over here. Okay, with respect to kpn. So of uv. Okay. So why this appeared once again? Because, like I said, on the backward pass, all 64 are contributing to each one of the kernel gradient values. So uv over here is one kernel value. Okay. So once we went over here, then because this is for one particular kernel value, okay, the summation uv will disappear. Whatever was the uv, only one value will be picked over here. Okay, because the derivative is with respect to the kernel, okay, this goes away. Whatever is the coefficient of it appears. And so the only thing we are left with is delta star multiplied by whatever this is, which is Cp of p, I minus u, j minus v, right? Okay, now what we did is we tried to look at it from a convolution equation point of view. If, like I said, if this was u minus I, if this was v minus j, this will be a perfect convolution between these two. But it is opposite sign. Okay, again, if we review some of the fundamental convolution concepts, we can switch it to opposite by simply multiplying it by a negative number over here. So then that becomes basically a rotation of this by 180 degrees. So the conclusion was that the partial L over partial KPQ or KIJ, whatever you feel like it, for the second layer is nothing but a convolution of delta star with the previous output Cp of 1. So this is our main conclusion. And this has to be rotated by 180 degrees. Okay, and then second part, I wanted to intuitively have you verify this was that does this result make sense? Okay, because the partial L over the kernel has to be a 5 by 5 matrix, right? Okay, so if delta star over here is a 12 by 12, 8 by 8, we already know 8 by 8. Cp of 1, we already saw it's 12 by 12. So if we do a convolution of 12 by 12 with 8 by 8, do we get a 5 by 5 answer?
Yes.
Yes, so it also proves that we are on the right track. Okay. Once we have the gradient with respect to the kernel, then, like I said, then it's easy. we'll update the kernel by the original value minus the learning rate times the gradient. And we keep doing that. Okay, so anyway, so now up to here hopefully makes sense. Okay, we also need to determine these biases over here, right? So let's take a look at these biases over here. How will they be accumulated over here? So it's very easy to see if I go back to the same equation, the forward equation, right? Now instead of taking the derivative with respect to the kernel, what will I do
To the bias.
with respect to the bias? Okay,
W1 will be delta star.
so then what happens?
Will be 1.
All of this disappears.
Just 1. And 1.
Bn is 1.
Delta star.
So what will be our conclusion for
Just delta star.
rotated by 180 degrees? Okay, so now partial L over partial B. Okay, this B we are talking about, B1 of 2. So B of whatever, N of 2. Okay, will be what? In this equation, like I said, instead of Cp of I minus U, J minus U, what will be left?
1.
Just 1. So what is that?
So delta star.
Summation of delta star. Because remember, delta is 8 by 8. You guys agree? So, does this make sense? How many values given one of these? Right? For example, if I pick n equal to 1, I'm trying to determine the gradient with respect to this.
1 value.
So isn't it a single value?
Yes.
So if I did the summation over here, you'll see it's a single value. Okay. And again, why is it a summation? See, in the forward pass, was it being added to every value, each one of those 8 by 8 values? Right? What's the meaning of this? Every 8 by 8 value that we computed, this is being added to it. So on the backward pass, we have to accumulate it. The gradients get accumulated. Okay. So anyway, see, that's why I was saying whoever came up with this should be given a Nobel Prize, because not only it is mathematically challenging, okay? So I'll give you my own example. So first time I went through many years ago, right? I read LeCun's original paper. Okay, it was written in I forgot, 98 or 99 or something like this, right? You read the paper, it makes really good sense, okay? But they don't give a single detail like the one we went through it, right? They knew it, but they didn't. Papers are very compact. So now I'm sitting and trying to program it, and I'm saying, how is it working? You know, I think, Michael, as you were, getting confused, same way I was getting confused too in the beginning. So it took me, first of all, a couple of months to really understand